Good morning, everyone, and welcome to EDP, an applied mathematics seminar. It's a pleasure for me to open session 36 of this seminar. Today, we have two excellent speakers, Jose Carrillo and Liliane Barrichel. Introducing Jose Carrillo, we have to Professor Max Souza. Thank you, Max. You can start.
Thank you, Juan. So it's a great pleasure to have Professor Jose Carrillo, who I know for quite a long time. He's an expert on PG, all sorts of PGEs and on applied on applications, going from nonlinear diffusion, hydrodynamic, kinetic equations. I mean, you name it. And Jose Carrillo has been quite a long time in Barcelona, and he then moved to a chair in Imperial College, and now he is at the beautiful city of Oxford, and next to the chapel, as I understood from our previous conversation. So that's quite a successful career, and he has too many distinctions. Maybe the one I could pinpoint is that he's now a member of the European Academy of Science, the mathematics. So by the way, he's now the head of the section, and he has been a fellow of the IMA and also foreign member of the Royal Academy of Science in Spain since 2001, I think. So it's a great pleasure to have you here, Professor Carrillo. And he's going to speak to us on nonlocal aggregation-diffusion equations, entropy, gradient flow, phase transitions, and applications. So thank you so much. The screen is all yours.
Thank you very much, Juan and Max, for the nice introduction. And let me then get into this interesting field of phase transitions. That's the main aim of my talk today. But I will get you through a bit of introduction of the field first, for you to appreciate and understand some of the results later. So then, first of all, I would like to talk about minimizing free energies, the general things that we know without entering too much in detail. And then I will concentrate in a very particular case of this phase transition that is called the Cooker-Smale model. And then I will talk mainly about linear diffusion case today and concentrate on the periodic boundary conditions in the next step. Okay, so the origin of the problem. The origin of the problem came from interacting particles. So the idea is that you want to minimize the total interaction energy of particles, and to deal with the evolution of particles that are subject to an interaction potential, but where the inertia term is assumed to be negligible. So that's why here, if I take as interaction potential W, which is in principle assumed to be a good function set at the origin, and if you want, think about it as a radial function, because most of my samples will be radial functions at the beginning. Later on, it will be a bit more even simpler, even smooth functions. But let's assume that you are given this W that is symmetric, or even radially symmetric, and then you can assume that the presence of each particle produces certain force at each location. So the presence of a particle at xj produces a force at xi, which is given by the sum of these interactions, which are computed by the gradient of the interaction potential in the direction of xi minus xj. So it's a kind of generalization of a kind of Newtonian interaction, if you want. But this is the total force, and then that's why I said about the inertia term that is negligible, assume negligible, because this gives you directly the derivative of the in time of the position of the particle xi. So I'm assuming that the second order dynamics, in the Newton equations, the second order derivatives is negligible. Okay, so I do this first order dynamics. Let's see quickly, one can guess what the equation at the macroscopic level should be. By the way, this simulation I'm showing you here is just a simulation for you to see that even for a certain particular easy potential W, which is a combination, is some hyperbolic arcotangent of something, then you can get equilibria, you can get stationary solutions which are unexpected or with interesting properties like this one. So as I said, one can write quickly what you expect as a kind of macroscopic description of the system of particles, because you think in terms of the density of particles at time t, and you mimic the how you compute here the velocity field felt by the particle located at position xi, you can mimic that by defining now the potential, the velocity field generated by the potential W in this form. So meaning that an infinitesimal part of the mass of rho located at position y produces a force at location x, which is given by minus gradient Wx minus y multiplied by the mass. Of course, you integrate to have the whole total force acting at position x, and this is what you define as the potential, as the velocity field. So in other words, the velocity field is minus gradient W convolution with the density rho, and then you would expect an equation of that form. So a kind of continuity equation where the velocity field is given by minus gradient of the potential convolved with the density. Okay, so also these models enters into a more general class of models that are usually referred as aggregation-diffusion equations, in which you have this non-local term in the velocity field, but also some a local term, which leads to either linear or non-linear diffusion. So this term can be also obtained in some kind of asymptotic limit from the non-local term. So typically choosing potentials which are repulsive instead of attractive. So you could play the game of dividing in W the attractive part of the potential from the repulsive part of the potential, and then localize the repulsive part to lead to some kind of nonlinear term like this. Okay, so if you want, just to summarize, you can think in terms of I have an interaction potential. I can model attraction only if you want by the W instead of having attraction and repulsion. And then let's assume that repulsion is modeled by the non-local term, the local diffusion term here. And then the nice question would be, if repulsion is modeled by diffusion, when do you have a balance between this repulsion and attraction by the non-local term? Okay, so how you can attack this kind of question? You can attack this kind of question from the perspective of the steady states of the system of non-trivial stationary states. And this equation has, in fact, a nice Lyapunov functional. The Lyapunov functional associated to that equation, in fact, it has a very interesting it has a very a lot of meaning from the physical or the application point of view, because if you think in terms of physics here, this term, first term that uses the interaction potential is just that the total interaction energy of the system, while the second one gives you the entropy of associated to the linear or nonlinear diffusion. If it would be linear diffusion, this is exactly the entropy term, which is a rho log of the density, log of rho. This is something that we did a long time ago, but this kind of, if you write this, if you use this Lyapunov functional to construct the velocity field, then the macroscopic equation I wrote here can be written in this way, which is quite appealing. It's written as a continuity equation, again, where the velocity field is minus the gradient of the variation of the energy. So in that sense, we say that this equation has a gradient flow structure that can be written much more theoretically and much more, in a much more rigorous way, but I will not use that. So the important thing is this equation is a kind of continuity equation where the velocity field is minus the gradient of the variation of certain energy. Variations, by the way, taken in such a way that you conserve the mass of the system. Well, this is the computation of the variation of that energy that leads this to this. And if you choose the phi related to P that appears in the previous slide, then you get this equation. So the phi that appears in the function and the P are related by this relation here. And as I said, if you just take linear diffusion at this point, and that would be that P is the log of rho, because you have a rho here. Okay, to get a linear diffusion, you will need to choose P log of rho, because then this will become minus gradient of rho divided by rho. You simplify the rho, and then you get the Laplacian. Then you get here phi equals rho log rho. Okay, good. And why is Alepo functional? Because I mean, you formally compute the time derivative of this functional along solutions, and assuming that you can do the integration by parts, you get this kind of decay. Okay, in which the variation, here you get rho gradient of the variation square. Okay, good. So, of course, if it's something that looks like a gradient flow, this equation, we know that finite dimensional gradient flows will typically lead to convergence to, I mean, stationary states are given by critical points of the functional. So then, at least you would like to find, and if they are stable, what you expect is that the dynamics will bring you to at least local minimizers of the functional. So what you want to find are local minimizers of this total interaction energy. Okay, and now I can be more precise about the question I said before. When there is a balance between attraction and repulsion, and when you model attraction by the non-local term and the repulsion by the diffusive term. And this is something that appears in many different fields and applications. So here I'm just listing several of them. Some of the first two probably very classical at this point. And the last three probably a bit less known or more modern applications of these ideas. Good. So just to give you a couple of examples, to be more, just to be more precise on what I just said, let me just give you one example in, well, a couple of samples in mathematical biology. This one probably is one of the most classical ones, is the cell movement led by chemical cues, so, or by chemotaxis. So essentially what you have is this kind of experiment, which you have some cells, somebody with a pipette is putting certain chemical, and then you see that the cells, they just direct their movement towards the source of that chemical substance. So of course we don't want to follow just 6-7 cells as in this case, but we want to follow a large number of them that is modeled at the population level through in this case this function n of tx. So the Keller-Segal model as classically was introduced classically in 2 dimensions, and it has this structure in which you have just the nonlinear, linear or nonlinear diffusion term to model, let's say, the repulsion or the volume effect of the cells, or even just noise, and the tendency to go up the gradient of the chemical substance is modeled by this term here. And in the original Keller-Segal model, the concentration, the chemical substance is produced by the cells themselves. So in some sense, this is the way in which the cells, they signal each other their presence. So that's why the C is coupled to the N in the easiest way, probably without the blue terms. Then you just compute in the quasi-stationary approximation C in terms of N by inverting the Laplacian here. So in fact, if you invert the Laplacian and you forget about boundary conditions and you do it in 2 dimensions, you will obtain C in terms of N by doing the convolution with the fundamental solution, which is the log of X. And if you substitute it then here, C, you recover an equation of the form I had before, where the interaction potential W is the logarithmic potential in this case. Okay, good. So now I'm going to show you a case with nonlinear diffusion. Sorry about the change of notation. This is a system now, it's a kind of the Keller-Segal model in 1 dimension, so the easiest possible situation. So, and with no flux boundary conditions. Okay, so what I mean is that I'm just taking a different notation to this, but essentially the same in 1 dimension with linear diffusion, sorry, nonlinear diffusion with exponent 2. Why I say this is nonlinear diffusion, because this first term, divergence of u gradient u, is the same as Laplacian of u squared divided by 2. So it's like a porous medium term for those of you that know about it with exponent 2. And this part is just the chemoattractant part. The V is the chemical substance, and it follows this reaction diffusion equation I just wrote in the previous slide. And as I said, let's put it with no flux on an interval. So let me show you first some numerical simulations that are done with some funny volume scheme that I don't want to describe in this talk, but it's quite accurate for this kind of equations. And let me start with something. Well, first of all, let me just realize that in this case, there is a steady state that is clear, which is the uniform distribution. So just constant. Here, the blue is the density, and the red is the chemoattractant. If you put U equals constant, B equals constant for certain constants, they you fix certain mass, they are obviously solutions of this. So let's take a small perturbation of a constant, and here I have this parameter chi that I'm going to change later on. I'm going to move later on. So let's take chi between certain values. In fact, chi is 4 here. And I'm doing a small variation of the constant initial state. And you see that this small variation, the constant steady state is not the stable stationary state, it's unstable, and what you have is a convergence towards this steady state that is the stable configuration, at least for those initial data. But you can ask yourself, is this the only one of the stable stationary state, and how many of them you have? To which you converge or not as t goes to infinity. Let's see that the answer could be more complicated. I'm taking the same value chi, and this is the initial data, which I now take symmetric on that interval. I'm far from being constant. But that one, it does converge to the constant. It will stop probably earlier than being constant, but believe me that if you continue running it, you converge to constant in this case. So the number of steady states can be, already in this case, you see that you can have more than one, and can be quite complicated even in a simple sample like this. This simple sample, in fact, can be computed explicitly. So you can find many stationary states. And then what happens is that you can realize about this more complicated picture. What you have is certain values of chi for which you have bifurcation branches, in the sense of, here I'm just plotting stationary states, okay? And some stationary state, and I'm not plotting all of them, because I will show you what is happening. Before this value of chi, before 2, there is only one stationary state, and it's the constant. Here I am just plotting the maximum of the steady state. The constant steady state is always there, it's a steady state, but in many cases it's going to be unstable later on. But then at this first point, there is a branch that appears that in which you have a one-parameter family of solutions, that this happens in this particular case in all those points. But then in each of the branches, you have certain steady states. This is the one that we saw the simulation before, which you converge to, let's say, half bump on one boundary. That if you go along with the larger value of chi, it's essentially that the steady state is getting closer and closer to a Dirac at the boundary. Then you can have this branch in which you have a double bump solution. That again, as you go along, it will be just being squeezed. Then you have this branch that corresponds to 1.5 bump, 2 bumps, and so on. So just to give you an idea that even in such a simple situation in one dimension, the number of states can be really very complicated. And what we want to know is until which point do we have the easy convergence towards equilibrium, at which point we have this bifurcation that we will call, in certain sense, a phase transition later on under certain assumptions. Okay. So let me give you then an example of phase transition for the Kukeles-Mail model, a bit more complicated. This is a model that comes from kinetic theory. So this is just to tell you the origin of the model. And then I will show you in the next slide the specific PD that I'm studying. This PD appears in some swarming problems in kinetic equations. It's not that important right now to explain the origin of this model, but the important thing is that I'm going to look at solutions of this equation that only depends on t and velocity variable. Okay, I'm not going to assume that depends on x. It's a kinetic equation, so it's an equation for a probability density in phase space. So it's more complicated, but I will just simplify immediately. As I said, if I look at the homogeneous problem, I look into this problem. And now let's concentrate on this one, because it's better to see the point I want to make. This equation essentially has three terms. You have the linear diffusion term in this case. The noise is strength is called D. Then you have the tendency this kind of force is a force that brings you the particles to velocity 1. So it's a kind of a confinement potential. And this one is the interaction now between the particles. Now we have to think about the velocity variable, that is what comes in the original model, as the position. Okay, it doesn't really matter. We look at it from the mathematical viewpoint. But this is now the interaction potential appears here, because the UF is an average. Is this moment, the integral of BF dV divided by integral of F dV. This, when you assume that there is no x dependence, this becomes a constant because this equation conserves mass. So in fact, it's just this average. Okay, the UF is just the mean of the distribution F. So in fact, you can write this equation in the form of what I wrote at the beginning by doing the following choices. The interaction potential is just the quadratic. And then if you just compute the gradient of this, it will be the convolution of this with V, and this gives rise to this term here. This is the linear diffusion term. And in this case, there is a confinement term in the sense of the gradient of a given potential, which is this one. It's a double well potential. So in fact, in this case, it's a bit more complicated than the first example I showed you at the beginning of the talk. You have a free energy that has 3 terms instead of 2. The additional one coming from this external potential that is double well, that has 2 minima. Okay, so in this case, the idea is that the interaction potential can bring you from one the interaction can be strong enough to produce something that only is concentrated, and the noise also for the smaller value of the noise, the interaction can be strong enough to concentrate the solution around one of the local minima of the confinement potential. Okay, so in fact, let's see how to do that, how to study that. Okay, so first of all, we can find steady states of this equation just by looking at when this psi is constant. If psi is constant, obviously its gradient is 0, so it's a steady state. So if we put this psi equals constant, given constant everywhere in the whole line, or in the whole RV, then we can invert because of the log and compute what the stationary state should be. So the F should be of that form. But of course, this is a self-consistent equation because the U depends on F. U has to be its first moment. It has to be the integral of F with respect to B. So how can we find then the stationary solutions? By looking at the zeros of this quantity. So the U must be a zero of this quantity. It has to be such that the integral of F is 1, or is a given constant. Here I normalize it. 1 over z is a normalization constant. So the integral of F is 1. So I look for then steady states of this form such that this integral is 0. So in some sense, we can reduce in this particular case the bifurcation question to look for zeros of a one-dimensional function. One-dimensional, I say, is two-dimensional with respect to the noise. Is in one dimension. Let's say that we are in one dimension, so that is the zeros of a one-dimensional function with respect to the parameter d. This is how can I look at it. And then in that case, we were able to show that this leads to a phase transition in the sense that there is a region of the parameter space with only one root, which is u equals 0. So this is which is quite, from application point of view, it makes a lot of sense. If the noise is very large, there is only one solution, which is Gaussian that has 0 mean. So there is no preferred direction. While if the noise is small, then you can have solutions with non-zero mean. So meaning that there are other preferred, there is a different preferred direction than 0. So either the particles will move to the right or to the left. And this, you can look at it also already numerically from this form by looking at the zeros of this function. You can see that for the large, you have an S shape. So there are 3 zeros. The u equals 0 that we saw was a solution. It does the job of the constant in the previous cases. And a certain value positive, and it's a reflection. And then when you decrease the noise, when you increase the noise, this is for a small noise. When you increase the noise, then the S shape is getting less and less prominent. At some point, it becomes radially decreasing, and then only the 0 is a solution. So in some sense, if you look at the value of u of the steady state as a function of d, you will get a bifurcation diagram of this shape. So you have always the solution u equals 0. The u equals 0, depending on another parameter I had in the potential, is stable or not after certain sharp value. And there is then a non-zero solution branch that bifurcates from those points at u equals 0. Okay. So this is just to illustrate this result. This is the stationary state that you get along the bifurcation branch in the case of linear diffusion and nonlinear diffusion, to show you that this happens independently of the fact that you have linear or nonlinear diffusion. And here I'm decreasing the value of the noise. I start from here, and then this is decreasing the value of the noise, increasing the value of the noise here. And then when the noise is large, then you have something which is radially symmetric with 0 mean. At the beginning, it's concentrated at a non-zero, not 0 mean. Okay. Okay, so in this case, we could do this because we had this very explicit, again, form of dealing with the stationary states. But we can ask ourselves the question of how can I find these number of steady states, these branches of a steady state, and the first point in which these branches appear in general. Can we find that in general? And we put ourselves in the most simple case, which is the torus, in the case of with periodic boundary conditions. And that's what I want to explain you more in general, and what I'm gonna give you some ideas of what we have been able to prove. So this is the more general equation that I'm going to treat in the rest of my talk today. So you have the non-local interaction modulated by this parameter that I'm going to call kappa. So kappa, if you want, is the inverse of the noise strength now. So it's just to modulate the interplay between attraction due to this term and the repulsion due to the linear or non-linear diffusion. Here I put a power. The power can be either 1 to infinity, and I consider it on the torus. And I'm talking about probability density solutions, so I'm normalizing everything to have interval of rho in the torus equals 1. And to have periodic boundary condition, the W has to be coordinate-wise even, that I can fix with zero mean in such a way that this is well defined. Okay, here I'm not going to put myself in any complication, assuming regularity of W. W is as regular as you want. Let's say C2. For instance, if you take W to be one Fourier mode, the negative, and you do it on the sphere, with the negative is in the minus here is important because it makes it, as you will see, it has an importance later on. So you just take this one. This corresponds to a very well-studied, well-known model in statistical physics for synchronization of oscillators that is called the Kuramoto model with noise, or the noisy Kuramoto model. And it was well documented and already proven long time ago that for oscillators, you increase the value of the interaction. You see that at some point you go from a uniform distribution on the sphere, and at some precise point that is called kappa c, then you get to something that is peaked around certain location. So some steady state, which is a kind of Gaussian peak at certain location. So again, this kind of change of behavior, this kind of phase transition, as is usually called by physicists, was described in this model. So this is an example of what I'm going to show you. And now I need some notation to show you the main results. So sorry about this notation, but it's just a notation for Fourier modes. So the Fourier representation I'm going to take, the Fourier modes WK, are constructed by products of cosine sines of 1, suitably normalized, and then here theta of k is just to take into account the different cases of having cosine 1 and sine. Then there will be some 2's here multiplying or not, but to have this normalized in L2. So okay, so these are the Fourier modes. So I would say that the potential is H stable if all its Fourier modes are non-negative. Okay. And in this way, you can separate, if you want, in a potential, the H stable for the H unstable part. But the important thing is that we will see that H stable potentials are the boring case, in some sense. Okay. So that's the first result that one can get. I mean, if you look at the free energy of both cases, either for the nonlinear or the linear diffusion, and if you look at the cases of H stable potentials, you can show that these free energies, they have a unique global minimizer that is given by the constant. I forgot to say that, but the constant is a steady state again of this equation for periodic boundary conditions. And the constant is just 1 over L to the D, to the dimension, and it will be denoted by rho infinity. Okay. So if the Fourier modes are all non-negative, then that's the global minimizer. And also it is the global minimizer if the interaction kappa is small enough. So even if some Fourier mode is negative, if the kappa is small enough, it can compensate then, and the interactions can be compensated by the noise, and then still is the constant is the unique global minimizer. How can we obtain and analyze how many states that we have in this case, and trying to answer further this question of phase transitions? So again, we look for an equation satisfied by the steady state. And the steady states in the case of the linear diffusion or nonlinear diffusion satisfy this kind of self-consistent relation. So in the case of the linear diffusion, which is the easiest to see, by something very similar to what I wrote before, then rho has to satisfy that is equals to e to the minus kappa w of rho normalized, so meaning that is normalized by its integral. And for the case of power loss, then you have something similar. Okay, I will not concentrate. I will concentrate much more on the linear diffusion today. So that's why I'm paying attention only to a case of linear diffusion. In fact, you can characterize steady states. So you can say that you have a classical stationary solution, or even it doesn't. In this case, with linear diffusion, it's all weak stationary solutions too, are characterized by either being zeros of this function that I wrote before, or they are critical points of the free energy. And the same happens for the nonlinear diffusion case. Remember the notation I just said in words before. The constant that is always a steady state is 1 over L to the dimension. And we want to see bifurcations and phase transitions emanating from this particular steady state. So the Kuramoto model, in fact, corresponds to a bifurcation of this type. If you increase the kappa for a while, you have only one negative Fourier mode. So for a while, you have only the constant steady state, and at a sharp value, you see a branch of steady states that are of this form, the cluster solution that we call. I mean, this is getting more cluster as you go along the branch, and getting flatter and flatter and going to a constant at that point. This is what we usually call a continuous phase transition, because the bifurcation, the first bifurcation point, the first value of kappa for which you have other steady states rather than the constant steady state is, I mean, it's continuous along this branch. Okay, so how we can find, first of all, how we can find these branching points. So this is the first question that we ask ourselves, and in this paper in collaboration with Wabalani, Pavliotis, and Slichting, what we did is to give conditions for phase transitions to happen. So we say that kappa star is a bifurcation point if for the solutions for the we are using u plus rho infinity. I mean, we use this notation to separate the constant. So this is like rho minus rho infinity. So we say that this point is a bifurcation point of this function. So we can find that this is a bifurcation point of this functional whenever we have a kappa star that is given in terms of any negative Fourier mode, and these two conditions are satisfied. Okay, so in short, any negative Fourier mode in W, which is what it means, this condition, leads to a bifurcation branch as soon as it satisfies this non-resonance condition. It can be, this condition can be understood as a resonance condition because it's the number of Fourier modes such that the value W hat K star divided by its normalization coincides with this. This is very much related with the application of Crandall-Rabinovich theorem. Crandall-Rabinovich theorem is a bifurcation theorem that tells you that you are going to have a bifurcation branch as soon as the kernel of certain derivative, Gateau derivative of the operator has dimension 1. And this has much to do with that condition. Okay, so now that we have understood the bifurcation branches, the same happens for nonlinear diffusion. So let's see what else we can say. What else we can say about the first time that you had your first bifurcation branch. We know that all negative Fourier modes leads to a bifurcation branch if that condition of non-resonance is satisfied. Now, what happens exactly at the first bifurcation branch, or even before, I would say, what happens at the first value of kappa such that you have another steady state at that value, because this could be before the first bifurcation branch. In fact, these kind of questions were already studied by several people. So here I'm just going to define what do we mean exactly with a transition point. So Chase and Panferov define what the transition point is, and they define it as this. So it's when before kappa c the constant is the unique minimizer of the free energy. In our case, I mean, they define this in general for an energy functional. At a kappa c exactly, still rho infinity is a minimizer of the energy. And for kappa larger than kappa c, there exist other densities that they are the different from the constant that are minimizers of the energy. And we can distinguish between continuous and discontinuous phase transition. So we say that discontinuous if at kappa c, rho infinity is the only minimizer of the energy. And when we take minimizers for larger values of kappa, as kappa goes to kappa c, then you get only rho infinity in some topology. Okay, so in that case, we will say that the transition point is continuous. Otherwise, we say is discontinuous. Okay, so I'm going to give you the two results that we prove in this direction with and explain it with pictures. We gave two regimes, we gave two theorems, one that implies that the transition point is continuous, and another one in which you prove that the transition point is discontinuous. Let me first concentrate on the right. So you have the nominal mode scenario, say that your first mode is negative and is much larger than the rest of the negative Fourier modes. This is the scenario like Kuramoto, in which you have only one. In fact, all the others, I mean, you have only one Fourier mode and is negative. That case leads to a continuous phase transition, always. And this case is a case in which there is some kind of resonance between several Fourier modes. So if you have several negative Fourier modes that are nearby in value, and also they satisfy certain relations between the case, then you have a discontinuous phase transition, meaning that the first point of kappa in which you have another steady state might be even before the first transition point, the first bifurcation point, sorry. Okay. So these cases, in fact, also happen for nonlinear diffusions. And yeah, how many minutes do I have left? Yeah, I assume that I have only 2-3 minutes.
You have 3 minutes, sorry. I was disconnected here.
That's fine. So then I would say, just to finish, that similar results to these conditions, to these if conditions for continuous or discontinuous phase transition can be given for the nonlinear diffusion case. But what we somehow observed is that, I mean, I don't want to repeat that. Yes, I want to repeat that. Yeah. So what we observed is that the near resonating dominant modes is this condition. This is the condition I simplified and illustrated in the previous figure. But what we see on nonlinear diffusions is that we can give ranges of M. In fact, we can prove that for M between 2 and 3, all transition points are always discontinuous. So there are no continuous transition points. While for M equals 4, we are able to show that for a large class of potentials, we have continuous phase transition. So still, for nonlinear diffusion, it's not that clear under which conditions you have either one or the other. But this continuous transition point seems to be more pervasive than in the linear diffusion case. So just I'm going to conclude. So just I hope that I convince you that this aggregation diffusion equation, despite their simplicity to be written, can lead to complicated phase transitions and bifurcation diagrams. We gave some general conditions for continuous or discontinuous phase transition depending on the interaction potential, and nonlinear diffusions lead to the persistence of these discontinuous phase transitions with respect to the case of linear diffusion. And I just want to thank finally my collaborators on these works that are the basis of this talk. Thank you very much for your attention.
Thank you, Carrillo. Thank you very much for your very nice, interesting talk. So I guess we still have time for 1 or 2 questions.
I would like to formulate some questions.
Sure, please.
Go ahead.
Okay, good afternoon, Professor. Professor, I would like to know if you investigate about the phase transition in DNA molecular.
In what?
DNA, in DNA.
Yes, yes.
Because I am working some topics about that, but your phase transition, I understand in your exposition is a relationship between dynamic and thermodynamic.
Yes.
That's the idea. But there is a problem in the probabilistic case interaction in that problem. The probabilistic, because the thermodynamic have the definition of phase transition, and dynamic you establish a bifurcation, or the resonance in that problem. I would like to know how I can to see the phase transition in biological problem, because for me this is driven by free energy, or entropy, the first order, second order.
Yes.
What if in your problem, because I see the movement of the molecule. Entonces, the new structure is the phase transition for you or the disorder?
Well, I mean, here I'm looking at the phase transition at the level of the continuous model, at the level of the density rho, and it's driven by the free energy, as you said, as you explained. So the question that you were asking me about DNA at the beginning is more related to a discrete model. Of course, these kind of questions, you can do them at the discrete model. So what I mean at the level of the number of particles. Typically for DNA, what people are trying to do is to look at the free energy of the system of the n the atoms that compose the molecules that they are looking at. And these are also what people do in protein folding or other questions. I assume that for DNA, I'm not aware of any particular work on that direction, but I assume that they are looking at similar viewpoint. The big difference also is that in that case, where you are typically talking about very singular potentials. And today I was talking about more smoother potentials. So what I mean is that typically in those applications, the interaction potential is going to be Lennard-Jones and super singular potentials at 0, which of course doesn't allow for any continuum modeling, but the discrete level is very interesting and very relevant questions.
Okay, I understand. Okay, I would like to write for your email for some.
Sure.
I would like to know.
Okay, very good. No problem, please.
Many thanks for your application, for the explanation. Thank you very much.
No worries.
Thank you, Hernan. Any further questions to Professor Carrillo? Well, I have a very simple one, which is, can these bifurcations be realized experimentally? Do you know any setting when you can actually realize?
Yes, for instance, this kind of this model that I was looking at, the Cooker-Smale model, is related to several other models like the beat-check model for swarming, and this kind of phase transition driven by noise has been reported in experiments with myxobacteria and things like that. Yes, so there are cases in which this is certainly seen in experiments.
I see. Thank you. So if there are no further questions, and I don't think there are any, so let's thank you, Professor Carrillo, once again. Thank you so much for this wonderful talk.
Thank you. Thank you for the invitation.
And I return to the host, Professor Juan. So
thank you, Mac, and thank you a lot, Professor Jose Carrillo, for amazing talk.